Hi all, it's Professor Marinos here again, and I'm really glad you're with me because today we're really going to get to the heart of thermochemistry. So over the last few lectures, we've described some concepts such as entropy and enthalpy that describe how the quantity and form of energy can change in any physical system. And today we're going to take these concepts and apply them to chemical systems in which a chemical reaction may or may not occur. And we're going to use these concepts to determine whether or not that reaction is going to occur spontaneously. And we're also going to use these concepts to determine where the equilibrium point for any given chemical system is. So let's launch right into it. So, for the learning objectives for this lecture, by the end of this video, you'll be able to calculate the standard Gibbs free energy of a reaction, and also determine whether or not a reaction is spontaneous or non-spontaneous at standard conditions. So, before we discuss whether or not processes will be spontaneous in a system, I think it's useful to give a pretty firm definition of what a spontaneous process is. And a spontaneous process is simply a process that will occur without extra energy input into a system. So a good example of this is I park my car outside all the time, and my car is getting rustier and rustier in these harsh Buffalo winters. And so that's a great example of a spontaneous process. You have steel being turned into rust. That is a process that will always occur in an atmospheric system of the Earth, and the reverse process will never occur. I'm very sad to say that my Mazda will never spontaneously de-rust itself. Another good example of this is you yourself, your bodily system. If you stop having energy inputs into your bodily system, you're going to die. God, that's so morbid. But yeah, if you're not busy being born, you're busy dying. And now, it's important to note that just because a reaction is spontaneous, that doesn't say anything about the rate at which it will occur. If I stopped eating food, I die rather quickly. I can leave my Mazda outside for, 3 or 4 more years before it's completely turned into rust. And another good example of this is perhaps the example of diamonds at the pressure of the surface of the Earth. They are spontaneously turning into graphite. But, actually I don't think this is graphite, I think that's coal, but bear with me. But you don't really have to worry about your diamond ring spontaneously turning into a lump of graphite. That process is occurring so incredibly slow that it'll be many, many lifetimes before you're looking at a ring with a nice lump of pencil lead in it. So anyway, let's continue on and see what we can do with this concept of spontaneity. Okay, I would just like to start off by restating the laws of thermodynamics. First law says that the amount of energy in the universe is invariant over time, or that the change in energy in the universe over any interval of time is 0. Second law of thermodynamics says that entropy is always increasing in the universe, or that delta S universe is always greater than 0 for any reaction going forward in time. So, how does this determine whether or not a reaction will be spontaneous in a system? Let's do some mathematical wizardry and try and figure that out. So to start off, let's delineate a system. We'll just draw a box around a system like I love to do. And that separates our system from its surroundings. And we'll say inside this system, there is some reaction occurring. Let's say that reaction is A plus B yields C. Now, actually, we don't know if this reaction is occurring in the system. But we know that if it is occurring in the system, that it must necessarily be increasing the entropy of the universe, because any process increases the total entropy of the universe. But we can partition that entropy between the entropy increase in the surroundings and the entropy increase in the system. So we know that if the reaction is occurring, it's either increasing entropy in the surroundings and or it's increasing entropy in the system. And so we can write the change of entropy in the universe as simply the sum of the change of entropy in the surroundings plus the change of entropy in the system. Now, let's consider entropy for a second. Entropy S, you'll recall, is in units of joules per mole per Kelvin. So the amount of energy produced per degree Kelvin per mole of product produced in the reaction. Now, we have a temperature dependency. And this temperature dependency means that if we can get this K out of the denominator, then we'll have an amount of energy produced by the production of entropy at a set temperature. And so what we're going to do is we're going to assume that the temperature of the universe is constant. Or at least we're going to assume that any change that's happening inside the system is not going to change the temperature of the entire universe by any appreciable amount. So let's multiply through by a constant temperature everything. And what we're going to end up with is T delta S universe on the left-hand side of this equation. And T delta S universe represents the amount of unusable energy produced through the production of entropy in the entire universe. And that's simply the sum of the amount of unusable energy produced in the surroundings and the amount of unusable energy produced in the system. You'll recall that we defined previously entropy as being related to the amount of energy that is unavailable to do work. And so that's what I mean when I say it's unusable. It's unavailable to do mechanical work in the system. And so now, let's see what we can do with this equation. Okay, so this equation represents the total amount of unusable energy in the universe that's created by a reaction occurring in our system. But now we think back to the first law of thermodynamics that says the total amount of energy in the universe is constant. So what this means is that if our reaction has increased the amount of unusable energy in the universe by a reaction happening in the system, that the amount of usable energy within the system must have decreased as a result of this reaction. So let's roll with that. So we have the formula for the amount of unusable energy produced in the universe. We can then calculate the amount of usable energy, or the change in usable energy, as a result of the reaction occurring, simply as the negative of that formula. So delta usable energy equals negative T delta S surroundings minus T delta S system. And we'll just go ahead and call this quantity on the left-hand side G. Now, consider this term right here, negative T delta S surroundings. This represents the energy transfer to the surroundings that resulted in the production of entropy in the surroundings. And in a closed system, the way that energy is transferred to the surroundings to cause an increase in entropy is by the transmission of heat. The system heats up the surroundings, makes those molecules vibrate more, and thus causes an increase in entropy. Now, think back to the last lecture, we had a quantity that represented the heat transfer between a system and its surroundings. That's delta H. So here we can see that the enthalpy comes into play. And we changed the sign because enthalpy is from the perspective of the system, but that quantity above is from the perspective of the surroundings. So now we can see that the change in usable energy in the system is driven in part by the enthalpy. And then we can just bring that other part of the equation down. And this is the equation for Gibbs free energy, or G, or the change in Gibbs free energy, I should say. And this equation is so central to thermodynamics, so please commit this to memory. Delta G equals delta H minus T delta S. The change in free energy in a system, or the change in usable energy in a system, is equal to the change in enthalpy minus the change in entropy times temperature. Now, if delta G is less than 0, this reaction is spontaneous. And this is because simply that if delta G is less than 0, then T delta S universe must be positive, and so the entropy in the universe is increasing. And so that is a spontaneous reaction that's going to occur because it's increasing entropy in the universe. If delta G is greater than 0, that's a non-spontaneous reaction. In fact, what that means is that the reverse reaction is going to occur instead. That means that C yields B plus A is a reaction that is spontaneous in the system. And finally, if delta G equals 0, that means that no reaction is going to be occurring in the system. That means the system is at a state of rest or a state of equilibrium. So That's the punchline of this lesson. If delta G equals 0 for a given reaction in a system, that means that that reaction is at equilibrium and it's not occurring. Okay, so I'm just going to write out this formula once more, just because it's so vitally important to you succeeding in thermochemistry. Delta G equals delta H minus T delta S. But how do you go about calculating these quantities? Well, delta H we covered in the last lesson. It's simply the sum of the number of moles of a product times the molar enthalpy of those products, minus the sum of the number of moles of the reactants times the molar enthalpies of the reactants. So we covered that. That's a terrible sigma, but whatever. And similarly, you can calculate delta S in just the same way. So delta S will be calculated simply by being the sum of the number of moles of a product times the entropy of that product, minus the sum of the number of moles of a reactant times the entropy of those reactants. And you'll notice that we drop the deltas from these S's because entropy is knowable in an absolute form, unlike H, which is not knowable in an absolute form. So, finally, if we consider this formula at standard conditions, we'll just put a little degree sign above all those. That just means that we're doing this equation at a temperature of 298.15 Kelvin, and with concentrations of either 1 molar products and reactants in solution, if we're talking about an aqueous equilibrium, or all gases at 1 bar partial pressure, if we're doing this in a gaseous system. And this is called the standard free energy. Now, as I said before, the enthalpies of formation and the entropies of various chemical compounds have all been determined at standard states, and these things you can just look up in a table. And so you can pretty easily, just looking up data, compute the standard free energy of reaction for most all chemical reactions. So what does this tell us? This tells us if a reaction will be product or reactant favored at standard temperature conditions. So you start off with parity in the system. You start off with equal amounts of products and reactants in the system. And if the standard free energy of reaction is negative, then you're going to be moving more towards the product side. The reaction is going to proceed in a forward direction. And if it's positive, you're going to proceed in a reverse direction. Now, of course, in the environment, most reactions don't occur at standard conditions. So, in order to figure out whether or not a reaction in the environment is going to be spontaneous or not, you need to make some modifications to this formula, which will be the topic of the next lesson. But first, I want to briefly explore some of the properties of Gibbs free energy before we move on to that. So here again is our equation for Gibbs free energy. And you'll recall that if delta G is negative, that means that the total amount of entropy in the universe is increasing as a result of a process described by this formula. And therefore, that process will be spontaneous. If delta G is positive, that means that the reaction will be non-spontaneous. But you'll notice that this formula on the right-hand side is comprised of 2 terms. You have the enthalpy term, and you have the entropy term. And each of these terms can assume either negative or positive values. And I just want to explore really quickly what it means if each of these is either negative or positive. So we'll start with the initial case of the enthalpy term being negative and the entropy term being positive. So you have a negative number minus a positive number. And that will necessarily result in a negative number for delta G. So therefore, any reaction where you have negative enthalpy term and a positive entropy term will result in a reaction that is always spontaneous. So this is a exothermic process that also increases the entropy inside the system. Now consider the case of an exothermic process that decreases the entropy inside the system. Well, you have a negative number minus another negative number, or plus a positive number. And so delta G will only be negative if the absolute value of H is greater than the absolute value of T delta S. So a big negative number plus a small positive number will equal a negative number. So how is T delta S, how is that a small positive number? That will only be a small positive number if T is low. So this is a reaction that is spontaneous at low temperatures, but non-spontaneous at high temperatures. And this is what we call an enthalpy-driven reaction. Contrast this with a case where you have an endothermic reaction, delta H is positive, and you're increasing entropy inside the system. This is the converse case where we need the entropy term to be greater than the delta H term in order to make delta G negative and make it a spontaneous reaction. And this is a reaction that will only occur when T is high, and this makes that whole equation negative. So this is an equation this is a reaction that would be spontaneous at high temperatures, and we call this an enthalpy-driven reaction. The change in free energy is driven primarily by the increase in entropy in the system. Finally, if you have a process where the enthalpy term is positive, so it's an endothermic process, and the entropy term is negative, so you're decreasing entropy within the system, that is a reaction that will always be non-spontaneous. So this offers a useful framework for considering the relevant temperatures at which a reaction will or will not occur, given a constant pressure. Okay, so that's all I have for you today. Today we learned about Gibbs free energy and how the Gibbs free energy determines whether or not a process will be spontaneous or not in a system. And I also said that if your system is at 1 bar pressure, 298.15 Kelvin, and equal amounts of products and reactants in your system to begin with, you can just use published values of the standard enthalpy and the standard entropy to compute whether or not your reaction is going to be spontaneous or not by computing the standard Gibbs free energy. So if all your reactions occur at 1 bar pressure at 298.15 Kelvin and equal amounts of products and reactants, then you're good. You can stop learning thermodynamics. You can just skip to the next lectures. But if your work exists in environmental systems that don't exactly follow those conditions all the time, we need to make a few modifications to those formulas to actually be able to describe whether or not spontaneous reactions will occur in non-standard conditions, which are indeed the conditions that you most likely find in the environment. So in the next lecture, we're going to launch into that. See you then.